Hi, thank you for inviting me to this talk. I just recently joined Google, actually, moved there from Monash University in Melbourne. So a little confused to what I was meant to say here, really, but I'll give it a go. So this talk, a little bit of it about, it's kind of based on some of the work that I did at Monash, and it's got a Google twist, which basically means, is it cost effective in reality? So I'll start off with this slide, and I like to point out kind of this is the speed or the trajectory at which the core speed per fiber is going at. It's consistently gone at an order of magnitude every 5 years, which just happens to be the same slope by the Ethernet. I don't really think that's a coincidence. So now we're at 2010, and we're almost up to, we're about 10 terabits. So we're still keeping track. But the next step might be difficult. And here's why. So, I mean, this is very elementary to most, so I'll be quick. So when we went from 10 to 100 gigabits per second, we exhausted all of the free dimensions of modulation. And we greatly improved our spectral usage to be over 50% now. So I'll look at some of the ways that, or methods that people have proposed to try to get beyond 100G, to trying to get a next 10x, so to get 100 terabits through fiber. And this, it's all kind of, getting more speed is just based on this very basic equation. We want to utilize our spectrum better, we want to get more bits per hertz, and we want more signal bandwidth. However, some of these methods really impair our reach, and as the previous speaker suggested, we need to increase our nonlinear threshold and decrease the noise in our system. And some of the things I'll suggest are not really new or sexy or even scientifically stimulative, but they're kind of the hard facts, really. So the obvious ways of increasing throughput is, of course, to increase the constellation size. Of course, when you do that, your constellation points get very dense, and you lose, or you need significantly more OSNR. In the case of going from 4 QAM to 16 QAM, you lose around 4x in reach. So we need to find ways of getting that back. We can also utilize our spectrum better. So currently, this is what we're doing, 30 gigahertz, 30 gigabaud in a 50 gigahertz grid. The around 40% of the spectrum is used to allow ROADMs to switch each wavelength to wherever it wants to go. Now, if we assume that we're going from origin O to destinations A, B, and C, and we want to get 100 gigabits to A, well, we'll just keep doing that. That's fine. So, in a flex grid scenario, though, if we want to get, let's say, a terabit to B, then we can reduce some of the guard bands because we're not using the ROADM capability, and we'll switch these wavelengths up together. In this case, it's at around, the channel spacing has decreased from 50 to 37, so there's some spectral saving there. And if, let's say, C was very close to O, then we can use a higher modulation format. The ultimate benefit, we can go from around 60%, which is where we're at, to about 80 to 90%, which is practically possible. And the WSS technology in the field today more or less allows this to happen. It does make network management more difficult, and it does make the system slightly more, if you have all of these, there won't be gaps in this in a real system, of course. And when you completely fill it up, it does have some implications in terms of fiber nonlinearity. And the idea of flex rate has also been thrown around. It's kind of similar to flex grid, really, except rather than reducing your bandwidth, in this case, you would increase your total throughput. And the third very obvious approach is, of course, to increase your total bandwidth. The fiber has very low attenuation over a very wide band, we've just sat at using the C band because that's the gain spectrum of erbium. But we have been better at extending the gain medium with different dopants in addition to erbium, as well as with Raman amplification, we can get more signal bandwidth. So in my view, bandwidth is really the most important kind of parameter that we have, because if you double the bandwidth, you double the throughput. The same cannot be said if you double the SNR, for example, by decreasing the noise figure of the amplifiers because of the Shannon's law capacity. And also, if you use more bandwidth, the phased array effect of nonlinearity is narrow band compared to kind of your WDM spectrum. So it has relatively small implications in terms of transmission performance. But all of these methods kind of make you lose some reach. And we can't, as we've already discussed, we can't just keep increasing the optical power because of current nonlinearities. I won't stay on this slide for too long, but that's the impairment. So one way that has been suggested and readily publicized on is digital backpropagation. We have one of the original inventors in the room, so hopefully he won't give me too much of a hard time. So the idea is you have a virtual link that somewhat is a model of your actual link, and you can undo the fiber nonlinear process of the real link by just sending it through the link, kind of the virtual link backwards. So the initial implementation was to do it digitally, so you have the real link, transmitter and receiver, coherent receiver in this case, and then you have the inverse fiber model here, which is implemented digitally. And the more steps you take and the wider bandwidth you consider, the more accuracy you can get in your compensator, and the better it will work. More recently, it has been suggested that you could bring this virtual link out the front of the coherent receiver and try to do it optically. That has challenges in itself, but you are able to kind of apply your nonlinear Schrodinger equation inversely on a wider bandwidth if you bring it into the optical domain. So the benefits of backpropagation can be very, very large if you allow yourself to take a very large number of steps and to take the whole kind of bandwidth that you're transmitting over. But this is not really a practical solution, because that also means that at your receiver or transmitter, or wherever you're doing your backpropagation, all of the digital signal processing that you're doing for all of the wavelengths that you're backpropagating for are required to happen on a single DSP unit, because you need all of the channels to know what all of the other channels are transmitting in order to get an accurate representation of all of the nonlinear effects. Also, this doesn't really work in a system with ROADMs, because your neighbors change throughout the link, and you don't always know where a particular channel was dropped, and especially you don't know what the information was transmitted on the channel that was dropped. So more realistic, we can more easily do backpropagation of a single wavelength. As you can see by the red curve here, the benefits are greatly reduced, especially if you go to higher modulation formats. And that's because of the cross-phase modulation effects or other interchannel forward mixing effects. So one way that you can improve the benefit slightly is to use perhaps a pilot tone. I've drawn it in the middle of the signal, but it could be anywhere really, has been shown to work on the side too. But the idea is you transmit this pilot tone and you go through your optical link with all of the WDM neighbors. You don't need to know what they are, but the crossface modulation will affect the pilot in a similar manner to the signal. And you get this phase broadening of both the signal and the pilot. Now at your receiver, I originally proposed to do this digitally. You would use a very tight, narrow filter to filter out the pilot that you transmitted with your signal. You conjugate that, and then you multiply that with the original signal. So by doing this, you clean up the crossface modulation that's common to both the pilot and the signal. Of course, the reality is with chromatic dispersion, they will be slightly different, so you don't get perfect compensation, but it does a good enough job to get you around a 1 dB performance improvement, which equates to around 20%, 20-25% in additional reach. In terms of complexity, most of it is in this filter here, which is probably similar length to your standard electronic dispersion compensator. Now, another way to decrease the complexity was proposed in Li Guifan's, which was to fold the backpropagation and use optical dispersion compensation. So here you have a dispersion compensated link, and you assume each link has starts with the same accumulated dispersion. And you backpropagate one span, and once you do one span, you multiply it by the number of spans. Now the problem with that is the crossface modulation is very large in your normal dispersion compensated systems. However, there are now available these channelized dispersion compensators using fiber Bragg ratings. So the idea of these is that the dispersion is compensated within a WDM channel, is undefined for some region, and then is defined again for the next WDM channel. But the relative channels in the dispersion compensator have very little difference in group delay. So the group delay of the different neighboring WDM channels is not compensated. And after a span plus a DCM, you get this stepped response. And what this does is it allows your WDM channels to walk off from each other, and you get the benefit of kind of like a phased array effect to minimize the cross-phase modulation. So this graph here summarizes the benefit. So you can see here, this is a rough estimate that I did that estimates the number of complex multiplications that you require to process one symbol. So this is with digital backpropagation in a dispersion uncompensated link, assuming one step per span. This is what you need for standard electronic dispersion compensation. And this is what you need for 8-step digital backpropagation, or folded backpropagation with these compensators. And this line here represents how much benefit, how much Q, which is a quantitative measure in dB of the signal performance. So you can see here, relative to what the standard systems are doing, we can gain around a 2 dB performance improvement with just this technique, with only around double the complex multiplies and the addition of the optical dispersion compensation module. Something else that I had to play with once in my life was the tuning of channel granularity. A lot of people have thought that it's better to use a higher baud rate, the highest baud rate as you can, to allow the dispersion to scramble your fiber non-linearity as much as you can. So we did this simulation where we fixed the total signal bandwidth to 400 gigahertz, and we simulated as many carriers as we needed to keep the data rate constant where you assume perfect Nyquist filtering and left no space. So the spectral efficiency, the data rate, the bandwidth is all the same. And we got this result. So depending on what your baud rate is, you actually get a slightly different nonlinear performance. So these graphs are in the nonlinear region. And as your link gets longer, it's actually more optimum to use more lower rate subcarriers. So you probably, in order to do this practically, you probably need a DAC at the transmitter and to generate your subcarriers digitally, because it doesn't make much sense to use an optical modulator every 3-point-something gigahertz. And the final way that I'll talk about is really obvious to increase reach is Raman amplification. So you use a different nonlinear process of Raman and you use backwards pumping to achieve distributed gain. I'm going through this really quickly because probably it's really obvious. I expected much more students in the audience. But the idea is, of course, you try to get as flat as you can with the power preventing it from dropping all the way to the bottom at the end of the span in lumped amplification. In terms of distance reach, ideally you can get more than 5x as predicted by these simulations done in Turin. Realizable, probably 2 to 3x in reality. And the good thing about Raman is it does give you more transmission bandwidth as well as increasing the SNR, although it is, of course, more expensive to install. Okay, so this is a summary of kind of all of the things that I've really talked about. You can see the numbers here, and the thing I want to, I guess, say is that none of them have a 10x next to them. So all of these fairly widely researched techniques are not really revolutionary. They're just kind of evolutionary ways, and in combination will probably get us the next 10x and get us to around 100 terabit per second in a single fiber. But we're still waiting for the next disruptive technology, and perhaps we'll find it in this workshop.